we only managed to cover one particular question. That is question 7 for or based on the group assignment. Now we will move into the next question based on the group assignment, which is question 8. Question 8 is pretty much the same with question 7. Means that both are focusing on hypothesis testing. In question 7, okay, we focus on the one sample test of hypothesis, while for question 8 we focus on two sample of hypothesis testing. So for question 7 we are focusing on chapter 9, while for question 10 we are focusing on chapter 10, the two sample tests of hypothesis. So if we can go back to another slide that discuss the two sample test of hypothesis, and if we can briefly do a little recap on what we have just discussed just now concerning the hypothesis testing. Remember that in hypothesis testing we have two contradicting hypotheses: hypothesis null and hypothesis alternative. Hypothesis null states the status quo, while the hypothesis alternative goes against the status quo. So status quo can come from relevant parties. For example, certain research group, certain trade group, if we are talking about business related matters. It comes from certain a news agency, for example. So all of this information can be used as the status quo, just like we have discovered, or just like what we have discussed before this, where certain trade group believe that the average spending for a family is equal to 606 in order to go back to school. That will become our hypothesis now. Hypothesis alternative, on the other hand, goes against the hypothesis null. Yeah. So in hypothesis null, if you have the terms like the hypothesis null states that population average value is equal to 606.0, so your hypothesis alternative will goes against that, where alternative states that population mean, population mean is not equal to 606.40. Same concept is shared by both chapter 9 and chapter 10, the one sample test of hypothesis and the two sample test of hypothesis. But the difference between one sample test and two sample tests is that in one sample test we are only focusing on one sample and one population, within one population only. I repeat, in one sample test we are focusing on the information that we obtain from a sample that we retrieve from one population. While two sample tests, on the other hand, in two sample tests of hypothesis, we have two samples that we retrieve from two populations. Yeah, we have two samples that we retrieve from two population. All right. So, and just like chapter 9, in chapter 10, we also have two hypotheses. Hypothesis null and hypothesis alternative. So, in hypothesis null, for two sample tests of hypothesis, we have these three different situations, just like in chapter 9. We have three different situations: two tail tests, one tail test. In one tail test, we have two different situations: right tail test, left tail test. Okay. In the chapter 10, we also have these three situations. Of course, right tail test, left tail test, both belongs to the one tail test. Yeah. But in this case, in the two tail test, we wanted to test. Okay. We wanted to test whether we reject the H null or fail to reject the H null. In a two-tail test, our H null states that population mean, okay, population mean number 1 is not equal to population, population mean 1 minus population mean 2 is equal to the hypothesized difference. Usually, this hypothesized difference is equal to 0. If it is equal to 0, that means mean for population 1 and mean for population 2 is equal to 0. In other words, there is no difference between mean for population 1 and means for population 2. Because when mean for population 1 minus mean for population 2, we have a result that is equal to 0. For example, mean for population 1 is 2. Same goes to mean for population 2 is also equal to 2. So 2 minus 2 is equal to 0. 0 is our hypothesized difference. But of course, hypothesized difference can assume any values. But normally, in the hypothesis testing, we always assume the hypothesis difference, this B subscript 0, as equal to null or 0. All right. Hypothesis alternative always goes against the hypothesis null. If the hypothesis null states that there is no difference between mean for population 1 and mean for population 2, hypothesis alternative, on the other hand, states that there is a difference between mean for population 1 with mean for population 2, because it is not equal to the hypothesized difference. So mean for population 1 may be larger than mean for population 2. Conversely, mean for population 2 may be larger than mean for population 1, as long as they are not identical. And of course, hypothesis alternative goes against the hypothesis null. And just like in chapter 9, you can also see these two symbols, equal to, not equal to. And remember, the equality always is null. So in the one-tail test, which we can divide into two subgroups, right tail test and left tail test. In the right tail test, we have the hypothesis null stating that the mean for population 1 minus mean for population 2 is either equal or smaller than the hypothesized difference. In other words, mean for population 1 is either equal to mean population 2 or mean for population 1 is smaller than mean for population 2. So that is what it means by this symbol here. So hypothesis alternative always goes against hypothesis null, where hypothesis alternative states that mean for population 1 minus mean for population 2 is larger than the hypothesized difference. So if this hypothesized difference is 0, that means mean for population 1 minus mean for population 2 is larger than 0. So in other words, this mean for population 1 is larger than mean for population 2, because if we subtract mean for population 1 with mean for population 2, we have a value that is larger than 0. It can be 0.1 as long as it is larger than 0. Okay, so that means mean for population 1 may be 4, while mean for population 2 may be equal to 3.8. So 4 minus 3.8 is still larger than 0, because we have a product, or we have a value of 0.2. So on the left tail test, on the other hand, so hypothesis now states that mean for population 1 minus mean for population 2 is larger or equal to the hypothesized difference. So if this hypothesized difference, normally we assume the hypothesized difference as equal to 0, you will be able to tell the hypothesized difference based on the statement that you have in the question. Yeah. But if we assume that this hypothesized difference is equal to 0, sama dengan sifar, that means this value over here, mean for population 1, is either equal to or larger than mean for population 2. So conversely, for the hypothesis alternative, we construct mean for population 1 that is smaller than mean for population 2 if this hypothesized difference is equal to 0. But of course, in business statistics, we normally assume that this hypothesized difference as equal to 0. Okay. Perbezaan yang dihipotesiskan bersamaan dengan sifar. Okay. The subscript 0 is the hypothesized difference between mean for population 1 and mean for population 2. Remember, in two sample tests of hypothesis, we wanted to compare the information that you obtain from population 1 with population 2. And just like in previous discussion, hypothesis null is constructed based on the information that we obtain from the status quo, while the hypothesis alternative is a statement that we construct that contradict with the hypothesis null. So hypothesis alternative will always goes against the status quo. Yeah. So if status quo states that population 1 is equal to population 2 in terms of value, so hypothesis alternative will always goes against that. It states that population 1 average value is not equal to population 2 average value. So if we are referring to the two-tail test. Same goes, you can also apply the same concept for right tail test and left tail test. I go back to our screen in order to see whether you are following me or not. Are you following me or not? Okay, all right, good, good, good. So we only have 45 students here, unfortunately. But don't worry, this session is recorded. The second part of the session is recorded, luckily. Okay. So, all right, we go back to chapter 10. So, another information that you need to know in conducting hypothesis testing is the information about the standard deviation. Yeah, the information about the standard deviation or the variance. Remember, if you know the variance or standard deviation of the population, In that case, you have to use the z value, just like what we discussed before this on chapter 9. Yeah, we use z value. We convert the x value into z value. That is used when we know the population standard deviation. But when you don't know the population standard deviation, in that case, you have to use the t value. Yeah, so you will use the t value in order to define or identify the probability. So back to this slide that we have here. So in chapter 10, we have three situations concerning on the standard deviation information. Number one, if variance or the standard deviation of the populations both are known, then the test statistic is assumed to follow the z distribution, and its value is calculated as z, that is equal to the difference between sample 1, okay, mean that we obtain from sample 1 minus mean from sample 2 minus the hypothesized difference divided by square root, okay, square root variance for population 1 divided by sample size 1 plus variance for population 2 divided by sample size 2. That is used when we know the variance for the populations, for both populations. Situation number 2. Remember, we are referring on the method to convert the x value into z or t value here. Yeah. So we will use this formula in order to convert the x value into z value when we know the population variances. Yeah, when we know the variance for both population. On the other hand, when the variance for both population are unknown, but we assume them to be equal, in that case, instead of using the z distribution, we are going to use the t distribution, and its value is calculated as t, degrees of freedom, is equal to mean for sample 1 minus mean for sample 2 minus hypothesized difference divided by square root. Here we have the variance, okay, for the sample. Okay, this is the pool variance based on the sample that we gathered. As 2 subscript p here represent the pooled variance. Okay, multiply by 1 over sample size 1 plus 1 over sample size 2. How do we obtain this pooled variance from the sample? Is by using this formula that we have here. Pooled variance is equal to sample size 1 minus 1 times variance for sample 1 plus sample size 2 minus 1 times variance for sample size 2 divided by sample size 1 plus sample size 2 minus 2. Yeah, and the degrees of freedom for this t distribution is equal to sample size 1 plus sample size 2 minus 2. So here we have the third situation where we don't know the population variances, and we also cannot assume that they are equal. Okay, we don't assume them to be equal. So in that case, we are going to use this specific t distribution value. So x1 minus x bar 2 minus hypothesized difference square root variance for sample 1 over sample size 1 plus variance for sample 2 over sample size 2, where the degrees of freedom is following this formula over here. All right, something that is much more closer to our question 8. Okay, so here we have an example. So this example is somewhat similar to question 8 that you have in the group assignment. Yeah, in this example we are also discussing, or we are also conducting the hypothesis test for 2 samples where we know the information about the population, standard deviation, or variances. All right, so here we have a situation where it is claimed that an average weekly food expenditure of the household in City 1 is more than that of household in City 2. Remember, a claim always belongs to the hypothesis alternative. A claim made by a research, a claim made by analysts. That analyst is usually you. Okay? The person who conduct the hypothesis testing is usually referred to you. You are the one that claim that the average weekly food expenditure of household in City 1 is more than that of household in City 2. So this sentence here will help you to construct the hypothesis alternative. Just as I mentioned just now, claim always belong to the hypothesis alternative. Once you have created the hypothesis alternative, you can directly create the hypothesis null. And as I mentioned before this, in order to determine whether you are conducting a one-tailed test or a two-tailed test, if it is a one-tailed test, in order to determine whether you are conducting a left tail or right tail test, you need to refer to certain keywords. In this case, we have these keywords: more than. More than means it is larger. The value that we obtain from sample 1, in this case city 1, is larger than city 2. And larger is pointing to the right. In that case, you are conducting a right tail test. A right tail test is a group belongs to the one tail test. Okay, so a survey of 35 households in city 1, and in this case, you can see that our sample size are not equal for both samples. Survey for city 1 has 35 households, while the survey conducted on city 2 has 30 households. Okay, so the sample size for city 1 is 35. The sample size for city 2 is 30 households. So let mu1, population mean 1 be the mean weekly expenditure for city 1, and population average 2. Okay, population mean 2, or the mean for population 2 is representing the mean weekly expenditure for city 2. So here we have an example, an information for city 1. The sample size obtained an average value that is equal to 164, the food expenditure, while the average expenditure based on a sample gathered for city 2 is equal to 159. And the standard deviation for population 1 is known to be 12.50, while the standard deviation for population 2 is equal to 9.25. This sigma here always represents the population standard deviation. Remember that. While if you have the lower s, that means you are given the information about the sample standard deviation. Remember, variance is equal to standard deviation squared. So if you have sigma to the power of 2 or s to the power of 2, that means you have the information about the variance. So sample size for population 1 is equal to 35, while sample size for city 2 is equal to 30. So here we have a number of steps that we need to follow. Yeah, of course we know we are conducting a right tail test. So the economist, which is you, wishes to determine if the mean weekly food expenditure in city 1 is more than that of city 2. In other words, we wanted to determine, or we are claiming that the average spending for city 1 belongs to the population 1 is larger than city number 2. So in order to construct the hypothesis alternative, you have these symbols over here. You have these components, which indicates that the average spending for population 1 or city 1 is larger than the average spending for city 2. While the hypothesis alternative always goes against the hypothesis null. Hypothesis alternative states that average spending for city 1 is either equal or smaller than the average spending for city 2. So just like previous discussion, for step number 2, you need to identify the significance level. Remember, significance level implies the probability of making a mistake, yeah, on concluding your hypothesis testing, yeah. It shows the percentage or probability of making an error in concluding your hypothesis testing. All right. So step 3 is to determine the p-value. So this p-value is determined based on the z-value. So just like previous discussion, in order to convert the z-value based on certain x value, in this case, our x value will be these two information here, 164 and 159. So in order to convert the x value into z value, there are certain formulas that we need to use. So for chapter 10, the hypothesis testing for 2 sample tests, there are that 3 situations that you need to know. Situation number 1 is where you know about the population variances. Situation number 2, you don't know population variance, but you assume them to be equal. Situation number 3, you don't know the population deviation or population variances, and you don't assume them to be equal. But in this case, we do know the population variance because we have the information about population standard deviation. So in order to identify the variance, we only have to square these 2 values to identify or establish the variance for city 1 and the variance for city number 2. In that case, we are going to use the z value. So this is the formula that we are going to use. This is the same formula, if I'm not mistaken, that you have to use in order to answer question 8. So z equal to x bar 1 minus x bar 2 minus hypothesized difference. Our hypothesized difference is equal to 0, okay? Because here we states that CD1 is more than CD2. So CD1 minus CD2 is larger than 0. So that 0 is our hypothesized difference, yeah? So that is how we know our hypothesized difference, by referring to the keywords as well. So divided by square root variance for population 1 over sample size CD1 plus variance for CD2 over sample size CD2. So 164 minus 159. So these information are obtained from this same table here. 164 minus 169 minus hypothesized difference that is equal to 0. Okay. So I hope that you are following me. If I can refer back to our Google Meet chat box over here. Yes, the reason why my voice got stuck is because of the internet connection. It can either be an issue of the internet that we have here in this institution, or maybe because that issue happens in your place. Yeah. But don't worry, this section is recorded. So if you miss anything, you can just refer back to my YouTube channel in order to confirm what we are trying to discuss here. Okay, so you guys are still following me, right? Because I don't want to be doing this by myself, you know, explaining the concept for myself. Okay, yeah, thank you. All right. So here we managed to obtain z value that is equal to 1.85. So this is the z value that we obtained, 1.85, right? So once you have obtained the z value, just like chapter 9, obtain the probability for that specific z value by using that normal distribution table that we have. If I can show you the probability for z when z is equal to 1.85 is 1.85. All right, so this is one of the examples of the distribution table that we can refer to in order to determine the probability based on specific z values. So 1.85, just to be confirmed, 1.85. In this case, okay, so this is the probability. When z is equal to 1.85, probability is 0.9394 or 93.94%. That is the probability when z value is equal to 1.85. Yeah. So 1.67, how do I obtain 1.67? Perhaps there is 1.85. Perhaps I'm referring to a different. Oh, sorry, yeah, 1.85. So this one, 1.85. So the probability when z is equal to 1.85 is 0.9678. 96.78% is the probability when z is equal to 1.85. Okay, so once you obtain the probability, you subtract by 1. You subtract by 1. Okay, so 1 minus 0.9678 is 0.0322. So this is the remaining probability. If we can say it in a layman terms, we can define this value as the remaining probability based on certain z value. In this case, based on z value that is equal to 1.85. So remember, when you are conducting a one-tailed test, multiply this remaining probability by 1. But when you're conducting a two-tailed test, multiply it by 2. So since based on the example that we have over here, we are conducting a one-tailed test. So we are going to multiply this remaining probability by 1. Yeah, because we are conducting a one-tailed test here. So we don't have the equal to and not equal to. We either have larger or smaller if not equal to. So that is the only what you call as symbols that we have or information that we have on the statement. So p-value is 3.22%. Once you obtain the p-value, we are going to compare it with the significance level. So since the significance level in this case is 5%, while our p-value is equal to 3%, we can say that p-value is smaller than the significance level. 3% is smaller than 5%, thus we reject the null hypothesis. Okay, remember, we reject the null hypothesis when p-value is either equal or smaller than the significance level. Conversely, we do not reject the null hypothesis when p-value is, sorry, if I can repeat it, yeah, we reject the null hypothesis when p-value is smaller than significance level. Conversely, we do not reject the null hypothesis when p-value is either equal to, if not larger than the hypothesis. If not equal to or larger than the significance level. Yeah, we reject the null hypothesis when p-value is smaller than the significance level. We do not reject the null hypothesis when p-value is equal to, if not larger than the significance level. So therefore, since we reject the null hypothesis, therefore at the 5% significance level, we can simply conclude that the average weekly food expenditure in City 1 is more than that of city number 2. Because this, once we reject the null hypothesis, we can simply accept the alternative hypothesis. Yeah, of course, there are only two results based on a hypothesis testing, either rejecting or fail to reject hypothesis null. But once we reject the null hypothesis, we can safely say that our claim based on the alternative hypothesis is true. In this case, at 5% significance level, the economist Yu concludes that the average weekly food expenditure in City 1 is more than that of City 2. You conclude that hypothesis alternative is true, where City 1 is larger than City 2. So do you have any questions so far? Do you have any question? One, yes. Thank you very much. Tan Mini 0.9674. Yeah, that is true. No question. So in that case, if you don't have any question, all right. We try to take a break for 5 minutes before we continue with question 9. Yeah, in question 9, we are going to discuss a different topic. All right, so we take a break for 5 minutes. Don't worry, for for question 9, we're just going to use, we plan to spend around 10 minutes because it is actually somewhat simpler discussion than question 8 and question 9. Yeah, don't worry. It is not going to take much of your time, yeah? So if those of you who wanted to stay, please, you're welcome to stay. But for those of you who cannot, stay because maybe you have some limitation or internet quota, in that case, you can just refer back to our YouTube channel, my YouTube channel, once I uploaded this recorded session. So if I can repeat again, yeah. While we are taking a break, if I can repeat again, remember, if p-value is smaller than the significance level, we reject the null hypothesis. Okay. If p-value is either larger than the significance level, if p-value is either equal or larger than the significance level, do not reject H null. Yeah. I repeat, if p-value is smaller than the significance level, reject H null. But if p-value is either equal or larger than the significance level, do not reject H null. Yeah. So if we reject H null, that means we conclude that H alternative is true. But if we fail to reject H null, that means we conclude that H alternative is not true. So while we are taking a break until 4 or 5. Any one of you who have any question, you can just post it on our chat box here. So for question, while we are taking a break here, for question 8, remember, as a tips for you, for that particular question, we do know the information about the sigma, about the population variance and population standard deviation. In that case, you are going to convert the x value. X value means the sample mean for both population into z value. Once you obtain the z value, identify the probability for that specific value, and after you have identified the probability, okay, determine the remaining probability, by subtracting 1 to that particular probability that you obtained. So multiply by 1 if it is a one-tailed test, multiply by 2 if it is a two-tailed test. So that is why it is very important for you to know whether you are conducting a two-tailed test or one-tailed test, because by knowing what type of test that you're supposed to do, it will help you to determine the actual value of the p, okay, the actual p value. Multiply by 1 if it is a one-tailed test, multiply by 2 if it is a two-tailed test, in the process of determining the p value. So if you have the words where you claim that, where your claim is larger than the status quo, that means you're conducting a right tail test. But if you claim that the information or the value is smaller than the value in the status quo, that means you are conducting a left tail test. So we are referring to chapter 10, chapter 9, and of course you can also use the statement, okay, in order to relate it with chapter 10. So 40 participants. Congratulations, you managed to stay until 4, which is very, very good. Yeah. You managed to stay until 4. So back to our session. So 38 participants left. All right. So back to our session. So last part. Okay, the last part for this session is where we will discuss the chapter. Sorry, we will discuss question 9. If I can show you an example of question that is quite similar to the question that you have in the group assignment. Okay, so all right, here we have a question that is similar what you have in the group assignment. Question 9, the situation is the following output summarizes a portion of. So question 9, okay, if we can, before I forget, question 9 is related to chapter 10, analysis of variance, or simply known as ANOVA. So here we have a situation. Experiment with no interaction. So in ANOVA, we can have interaction or no interaction. But in this particular situation, so this ANOVA is focusing on the no interaction. Yeah. So factor A consists of 4 kinds of organic fertilizer. Factor B consists of 3 different kinds of soil acidity levels. And the variable measured is the height in inches of a plant at the end of 4 weeks. So in the analysis of variance, we wanted to determine whether a certain factor can contribute, okay, to a certain result. In this case, the result is, or the product is, the height of our plant. And the factors that we have based on this particular question can be divided by 2, factor A and factor B. Factor A belongs to the types of organic fertilizers used, while factor B belongs to the different kind of soil acidity levels used. So we wanted to determine whether fertilizer and acidity level can contribute or can influence the height of our plant or not. So that is the purpose of conducting the analysis of variance, identifying whether certain factors can influence certain result or not. Yeah? Identifying the relationship, if we can call it the relationship between dependent and the independent variables. So if we can call it that way. So in the analysis of variance, we wanted to determine whether our dependent variable, in this case, the height of a plant, is influenced by 2 independent variables, the organic fertilizer and the soil acidity level. Okay, we wanted to the independent variables can influence the dependent variable or not. So based on the sample that we obtained, so similar to your question, we have somewhat modified table in this session. So we have a number of sources of variation. So we have 3 sources of variation. First source of variation comes from the type of acidity level in the soil. Second source of variation comes from the fertilizer, from the type of organic fertilizer used. And the third source of variation comes from the error. The error means source of variation that don't belong to acidity as well as fertilizer, but contributes to the height of the plant. So you have other factors that may influence the height of the plant apart from acidity as well as fertilizer. And these are the sources is grouped into the third source of variation that we call as the errors. Okay, so this is the first what we call as column that we have in this table, which shows the source of variation. Yes, so the source of variation, we go back to that particular question. The second column shows the sum of square for each source of variation, for each factor. Factor B, which represent the acidity level, has this sum of square that is equal to 0.13, while factor A belongs to fertilizer has a source of variation that is equal to 44.25. So the sum of square for fertilizer is larger than the sum of square for the acidity. Okay, so this sum of square. Errors has a sum of square that is equal to 1.88. So if you sum up this sum of square, it will equal to 46.26. This, on the other hand, the third column shows the degrees of freedom, DF, degrees of freedom. So the degrees of freedom is equal to the number of, okay, so here we have the number of organic fertilizer. In this case, 4 kinds of organic fertilizer minus 1, you have the degrees of freedom for fertilizer that is equal to 3. While the degrees of freedom for acidity is equal to 2. And we obtain 2 by subtracting this kinds of acidity level for soil, 3 kinds of soil acidity level minus 1. You have the degrees of freedom for acidity level that is equal to 2. 3 minus 1 equal to 2. 4 minus 1 equal to 3. And we also have the information. Luckily, in this case, we have the information about the degrees of freedom for the error that is equal to 6. So if you sum up, you will be able to obtain total degrees of freedom that is equal to 11. Okay, 6, 3, 2. The next column is where we have the mean square for each source of variation. So here, mean square for factor B, mean square for the acidity level. In order to determine the mean square for factor B or for the acidity level, all that you have to do is to divide the sum of square by the degrees of freedom. So sum of square for acidity 0.13 divided by degrees of freedom that is equal to 2, you will have the mean square for factor B or the mean square for the acidity level that is equal to 0.065. Okay, so 0.13 over 2 is equal to 0.065. So we repeat the same procedure. You will be able to construct the mean square for fertilizer or the mean square for factor A and the mean square of the error. Yeah. So 44.25 over 3, we have 14.75. 1.88 over 6, you have 0.3133. All right. So the next column, we have the F value, okay, or F statistics. So this is the F statistic for factor B. Factor B here is the acidity level of the soil. So in order to determine the F statistic, all that you have to do is to divide the mean square for each factor by mean square of the error. For example, 0.065 divided by 0.3133 is equal to 0.208. So here, meanwhile, the F statistic for factor A, which is the fertilizer, is 47.08. So it is the product of a division between mean square for fertilizer with mean square of the error. So 14.75 over 0.3133, you have 47.03. So all right, the p-value, the p-value, it is actually somewhat simpler to determine the p-value if you are using, there are two ways to determine the p-value. Yeah, there are two ways to determine the p-value. One is where you on the F statistic from the F distribution. Yeah, F statistical distribution. The most simplest way is if you refer to many types of statistical software or statistical calculator that we can get online. Okay, in other words, there are various types of statistics calculator that you can use online in order to determine the probability or p-value based on certain F statistics. Yeah. So here you can simply type p-value calculator. Okay, p-value calculator. So we have many what you call as types of calculator that you can use. Say for example, we use this one, belongs to GraphPad. So here we have a free web calculator that can help you to calculate the p-value for certain F statistics. Okay, in order to solve the ANOVA table. So here we can convert the p-value from certain z, just like before this. Remember when we try to answer question 8 and question 7, we use manual, what you call as a method by referring to the distribution table. So apart from using the manual method, you can also use the online method. Means you can use online calculator in order to determine the probability, in order to determine the p-value for specific z, t, or f statistics. So here we are going to use the third what you call option here, converting or identifying the p-value for certain f statistic. So here, say that we wanted to determine this p-value over here, 0.818. In order to get this, all that you have to do is to plug in the F statistic for factor B, in this case 0.208. So plug in that information, 0.208, okay. 0.208, that's the first information that is required. Second information is the degrees of freedom. Okay, the degrees of freedom for that specific source of variance. In other words, degrees of freedom for factor B. In this case, the degrees of freedom is equal to 2. Okay, so this is the degrees of freedom, 2. Degrees of freedom is equal to 2. And then the third information is the degrees of freedom of, in this case, if I am not mistaken, the degrees of freedom for the error. In this case, 6. Let us see if we can get 0.818. 6. Compute. Okay, so here we have 0.8178, or in other words, 0.8. P-value for acidity level is equal to 0.818, while the p-value for fertilizer is equal to, remember to refer back to the F statistic for fertilizer, 47.08. We plug in that information, we click back, plug in that information. So the F statistic for fertilizer is higher than the F statistic for acidity level, 47.08. 47.08. So the degrees of freedom is equal to 3, and the degrees of freedom for fertilizer and the degrees of freedom for the error is equal to 6. So we maintain this value, compute. You have the degrees, you have the p-value that is equal to 0.0001. So that is how we obtain this value here. Yeah, 0.001. So A is fulfilled, completed already. If you complete this table here, you successfully completed question 9A. For question 9B, at 5% significance level, can you conclude that the average growth of the plant differ by the organic fertilizer? So here, so the question wanted you to come level. Remember, yeah, the p-value. Here, our p-value is 0.0001, and it is smaller than 0.0001 is for sure smaller than 0.05. Okay. So thus, we can conclude that the average growth of the plant differ by the organic fertilizer. Remember, yeah, our hypothesis, if we can call it a hypothesis, yeah, our hypothesis null states that the average growth of the plant is alternative states that the average growth of plant differ organic fertilizer. In other words, the organic fertilizer doesn't influence the height of the plant, while the hypothesis alternative states that the organic fertilizer influences the height of the plant. So here, since p-value is smaller than the significance level, we can safely say that we reject the H null, and we can conclude that the organic fertilizer influences the height of the plant. Or you can also conclude that the average growth of the plant differ by the organic fertilizer. So for question C, on the other hand, our hypothesis null states that the average growth is not different based on the acidity level, while the hypothesis alternative states that the average growth of the plant differ. Differ means they are not equal to, remember. So here we have the hypothesis alternative already. Okay, so the hypothesis alternative states that the average growth of the plant differ by the acidity level. So for question C, if you can compare, our p-value is equal to 0.818, and of course it is larger than 0.05. Since it is larger than the p-value, yeah, since it is larger than the p-value, since it is larger than the significance level, so if I can use a more correct, what you call as a symbol here, so did I take some time? Since the p-value is larger than the significance level, we do not reject the H null. Since we do not reject the H null, we cannot that the average growth of the plant differ by the acidity. Not conclude that the average growth of the plant differ by the acidity level. Okay, so